So now that we understand how to calculate covariance and correlation, uh, what's the purpose and use and specialty of correlation that is so useful? Well, we can think of correlation as a standardized covariance, whereas covariance allows us to kind of know the linearity, right? Are the points aligned in some sort of a linear fashion? We can think of it that way. But then the magnitude of covariance is a bit dubious. It's a bit hard to interpret. Is it strong? Is it weak? Very hard for us to understand. Yeah. So one example that I brought up earlier on is to find the covariance of airline mileage points with the market value of the free ticket that we can exchange the points with. So if they say use 1,000 points to exchange for a ticket from Singapore to Kuala Lumpur, and that we find out later that is worth a market price of say $300, then is this scaling proportionately? Yeah. So if we are using 10,000 points, are we able to get a free ticket that is worth, for example, $3,000? So trying to find that linearity, that proportionality, is one example of why we want to use covariance. However, is this proportionality strong or weak? Like some tickets, yeah, they actually scale, they follow this scaling, but some other tickets, tickets, free tickets that we claim using points, they don't quite follow, right? So there are weak proportionality and strong proportionality. But the resulting descriptive value that covariance provides is very hard for us to interpret because strong linearity can be a small number in covariance terms or a large number. And likewise, a weak linearity can be large or small. We just can't tell. And if you change the units, like instead of dollars, you measure in cents, that shouldn't change the linearity, the proportionality at all, right? But the covariance value will vary a lot. Yeah, because we're using length times height of the areas, right? Remember, so the units will change, will affect the strength of covariance. So all these kind of weakens the usefulness of covariance, even though we are very excited by the fact that covariance indeed does quite a good job in reporting the presence of linearity. So correlation is our savior. By dividing by the standard deviation, we standardize all covariance, no matter whether you find the covariance of points with dollars or Singapore dollars with Japanese yen, US dollars with uh, Europe's euros, and any covariance when we standardize it using correlation can be nicely interpreted because correlation standardizes the resulting value, resulting descriptive, to between -1 to 1 all the time for any pair of x and y. That's really, really powerful and useful because we can now associate quite good theoretical interpretations to these extremities. No correlation value will go below -1 or beyond 1. That's really nice. So what do they mean? Values close to 0 implies little to no linear correlation. Linear is very important here. We should always stress that. Yeah. Sometimes in our discussion, we conveniently kind of silently drop the linear word, but it is important to always keep in mind that when we say there is strong correlation, it is strong linear correlation. That means we are saying there's strong presence of a line. We are not saying anything else. We are not saying anything more. We are not saying anything less. So just a line. So when there's close to 0, we say there is no linear correlation. But we don't say that there is totally no relationship. It could really be noise. So it can cover the case when there is actually no relationship, Or it can cover the case when there is other relationship, like kind of a circular relationship, which is not a line or not easily represented by a line, but it is of certain very strong relationship, right? So because it's circular, you need certain certain force or certain behavior to make it circular. So uh, if you get data points lying in the circle and you calculate correlation, which tries to find any line occurrences, you're going to get the answer 0, which is true because it is saying that there is no line to represent a circle. Yeah. So be very careful about concluding that there is no relationship. That's not true. All we can say is that there is no linear relationship. No linear correlation is even better. When value of correlation is close to +1, we can say all these words. Strong, right? Because it's +1, the magnitude is large. It's positive. That means the larger the x, the larger the y. So it's like a positive gradient thing. That's of course implied by the covariance. And it's linear correlation. So we can say all these 4 words and not more and not less, right? So when we get a +1, it says a lot. Strong, positive, linear correlation. Likewise, when we get a -1, we can say a lot. Strong, negative, linear correlation. The larger the x, the smaller the y. So for example, if we get a +1 between height and weight, the taller a person, what happens to the weight? The heavier the person weighs. That's right. But if we go to another country or with another sample, we calculate the correlation and we get a -1 or negative 0.99 something, then we'll have to conclude that the taller the person, the lighter is the person. The other way around, the heavier the person, the shorter will be that same person. So that's negative correlation. So that's nice because it allows certain predictability, right? Let's say it is easy for us to judge a person without asking by visual inspection of their height. If we estimate the person to be tall, let's say 1.9 meters, and we get a positive correlation, we know that in this country, in this locality, these people, they have strong positive correlation, like +1. Then upon knowing that the person is tall, we'll say, well, we know right away that the person is likely to be very heavy, right? And so this allows for prediction or estimates of the property or aspect of that same item, the person's weight, that we are unable to measure. And it's not nice to ask, how heavy are you, right? So knowing correlation is kind of a key to finding indirectly another aspect of an item. And this often comes in useful because measuring one aspect of an event, of an item, of an entity, of a property, of a virus, of a whatever may be easy, but another aspect may be very extremely expensive, difficult, or even impossible. It takes eternity to come to fruition. For example, suppose under ultraviolet light, right? uh, the shinier the virus appears in microscope, the more contagious it is. There's a strong positive correlation, like plus 0.85, which is pretty large. What can we say when we look at another new virus outbreak? We look at it under UV light irradiation. It appears very bright. What can we say about the level of contagiousness of this new virus? Well, okay, yeah. So we can then, without waiting for the virus to spread and know that it is contagious, we can already get ready because we know it's very contagious. So it is nice to know this connection, this correlation, if it exists. And if it doesn't exist, it's not to say that there's a failure because we know then that measuring this has got no effect on that, and which is a nice thing to know sometimes. For example, in doing business, if the correlation between the price and the items sold is nearly zero. Okay, so for example, luxury goods. The higher the price tag, because we keep adjusting that luxury watch to higher and higher prices, the monthly number of watches sold is sometimes higher, sometimes lower, but doesn't change much. Constant, remember? So the correlation between the price, which fluctuates, and the number of watches sold is which is constant, is zero, because we know that the covariance is zero, hence the correlation is close to zero. So then what does that mean? It means that for luxury goods, well, we can just if we like and can account for it, can explain it, we can increase the price a little bit more without worrying that it will sort of tame the demand, right? So all these are good to know depending on the situations and occasions that we are talking about. So right now I want to sort of bring back our familiar diagram over here. And let's just quickly look at the correlation. Yeah. So for correlation, we already talked about correlation. Yeah. Correlation. Typically, we will be talking about rho, the population correlation, but oftentimes we will operate on samples. So let's use R. So for R, the sample correlation, we know that it is from -1 to 1. All right, and then it will of course go via 0. And for covariance sample x and y, it will go to -infinity all the way to 0, and then to positive infinity. Okay, now when R is -1, the data points will appear, or will almost always appears as something like this. Okay, so the gradient is negative, or something like this. Okay, so or something like this. So it's perfect. It's perfectly on the line. But when it is somewhere in between, so we're not talking about the gradient, all right? So R, when it's -1, will be the data points will be perfectly lying on a line. It's not to say that the line has a -1 gradient, -2 gradient, or so on. Okay, so it doesn't mean that. Gradient is gradient, R is R. So when R is -1, we know the points lie on a line, exactly on a line. Whether the line is nearly horizontal, nearly vertical, we cannot tell. We have to calculate the gradient. That's what gradient is for. But it is so R tells us the the lining up of the points. R doesn't tell us the gradient of the point. So need to be careful there. If R is +1, then the other way around. We know that the data points all line perfectly on a line that has a positive gradient, or this gradient, or this gradient. Okay, so let's just draw a cleaner one. So it is on this gradient. So they are all perfectly on the line. Not necessarily equally spaced apart, can be mostly concentrated in the middle, a few points here, a few points there. But when you look at it, it's perfect because it's perfectly +1. You cannot exceed +1, right? So when all the points without deviation from that line gradient is exactly lined up that way, then it is +1.